So next up, we have David Hughes from the Graphable, and he's going to be talking about composite queries for multi-domain knowledge.
Great. All right, we'll go ahead and get started. Hi, thank you for joining me today. Hopefully this is loud enough. Everyone can hear me in the back. I think so, because I hear some echoing anyway. Today, we're going to talk about two concepts, graph query engines and composite queries, and how those composite query capability is enabled by the concept of a graph query engine. We'll define what a graph query engine is, and throughout the discussion that we're going to have in this journey is we're going to try and prove the point that graph query engines are, in some perspectives, pivotal and change how we think about graphs. We'll look very briefly at the history of how we have come to having graph query engines and some of the challenges that both composite queries and graph query engines address that we see in today when we try and move a graph project into production. Then we'll look at how to implement composite queries using a graph query engine. And we'll look at two concepts in particular. One is schema-on-read, which is an inversion of what we know today in most of our graph projects, which is schema-on-write. And then also this broader concept of single copy analytics. So this diagram shows two things that I think are interesting. One is this green trend line that is the popularity of graph databases. Graphs have been certainly gaining in popularity, and I'm going to emphasize the word popularity over the last several years, but there's certainly been some barriers of translating popularity into actual adoption. And today I'll invite you to show up at a talk, I think 2:30 from Maya, which is going to talk about that popularity and growth of graphs, but maybe what we're not seeing with adoption in the jobs and engineering that comes along with that. This graphic is a couple of months out of date. I think that with some of the integration that we're seeing in graphs around concepts like in Gen AI, like RAG, retrieval augmented generation, that this inflection is probably a little bit more positive. Certainly that could be buoyed or supported by the fact that even though it's low here at the bottom of this graphic, we see that vector databases are, of all of the graph technologies, the ones enjoying the most positive inflection right now. And that's just at the bottom of that yellow line. Certainly though, what's driving a lot of the growth in the popularity of graphs is that more and more our world is connected. There's nothing that happens on this planet that doesn't affect each of us. And because of that, as a corollary, our data is more connected. And because of that, we see that there is value in looking at our data through a graph lens. So graphs have been around for a while. Certainly graph query engines in some perspectives have been around for a while as well. But it really was in the 2000s that a lot of that foundation was laid. I won't go into too much detail other than to say that now more recently we're seeing some newer concepts really start to surface. Earlier you heard a great talk on Quine, and that is around streaming graph analytics. We also have high performance graphs in Altipa, but also not on this slide, we're seeing things that concepts around Graph HD, if anyone has heard that, where you can create an embedding for a node and an embedding of the relationships between nodes, and then a hyper embedding for the entirety of the graph, and then using hyperdimensional math doing actual graph analytics and queries. So we're seeing a lot of novel new concepts come out about graphs. And one of the things that we're seeing is just like in the traditional database world where we're seeing a decoupling of compute from persistence of data, we're seeing the exact same thing in the graph domain as well. And today I'm going to use PuppyGraph, which is a standalone graph query engine, as a reference or an example for where we're seeing that same kind of decoupling in the graph domain. We should start off with what an understanding of what is a graph query engine. Quite simply, much like you think about Dremio in the traditional database world being a decoupling from persistence, here we're focused on a standalone solution that performs query compute or computation separate from how the data is stored. And we'll see in some upcoming slides some of the capabilities and features that allows you to have and enjoy when you have that decoupling. Now, Why is this needed? We'll also discover or dive into that a little bit more deeply in an upcoming slide. But in general, having an abstraction away from how the data is persisted allows users to have a lot more freedom about using the data as it is at rest and in different formats. And then I mentioned that we're going to use PuppyGraph as an example of this. There are some other technologies out there, but this one is the first mover in this domain, and I think a great example of what we're going to be talking about and how to actually implement composite queries. Let's go over some of the features of a graph query engine and how that enables composite queries. First, the biggest barriers that we see today in moving graphs into production and out of a proof of concept is the ETL conversation. It's great. I see it all the time when working with the companies that they're very interested in graph. They understand the concept of elevating the relationships between their data to first-class citizenship. There's a lot of value there. They understand that their use case likely is very graphy, but ultimately the conversation comes to, we now need to take a copy of your data and ETL it into a persistence layer. And there's all sorts of challenges there, not only technologically, there is regulatory concerns, there's cost, there's licensing, there's many things that represent that as a barrier. Also, consumable data sources and having multi-language query capabilities around different SDKs, that's implemented in today's graph databases. But when we have a graph query engine, you can start to have these kind of modular adaptation and flexibility to more quickly iterate on bringing in new capabilities and ways of working with your graph data. The 2 points though that I want to focus on this slide are number 4 and 5, and this is the concept of schema-on-read and also single copy analytics. Today, when you're working in most graph implementations, it's a schema-on-write framework or paradigm. You're going to take your data from some data sources and you're going to persist it after going through a modeling exercise and then ensuring that your model maps to your use case. You're going to then persist that data through the model into some graph representation. Schema-on-read inverts that concept. Your data at rest is sitting in various types of layers, and say it is a Parquet file in S3, a tabular store in Apache Iceberg, could even be a Postgres database. Now you're going to read that data from its source through your schema and then work with your data that way. So that's this inversion of schema-on-read versus schema-on-write. And what that allows is the next point, which is single copy analytics. Your data sitting in a tabular or a columnar store can now be seen through multiple lenses. That is a unique property because now you have your BI or your business intelligence teams being able to use SQL or the tools that they're comfortable with to look at the data in an enterprise or a company or a project. And you also now have a team of graph engineers and people who want to look at their data through a graph lens, able to work on that exact same data. There's not a question of ETL or lagginess between the truthiness of the data, between the source data and what's been persisted in the graph. It's all the same data, now being able to put on multiple lenses so that you can interpret and try and surface intelligence from the data that you have. So briefly, these are the foundation for what I want you to have in mind as we start thinking about an implementation of composite queries using a graph query engine. PuppyGraph, this is their model and architecture for it, where you have multiple different data sources. You can see these on the bottom, and ultimately those bubble up through a physical and logical representation and ultimately return a result to a user. One of the advantages that I want to point out here is at the query planning process. Now a graph query engine can leverage the capabilities of how the data is stored. And I'll look at or mention Apache Iceberg as an example. Apache Iceberg has expressions. You can leverage those expressions during query planning, as opposed to when you have your data only sourced in one kind of persistence layer. As you represent and create a query and plan for it, you can take advantage of any of the capabilities at the persistence layer. All right, so let's get started on an implementation because I want to make sure that I save enough time for questions. That's the foundation of a graph query engine. So now let's move into the core of the talk, which is composite queries. This is and I apologize for the size, probably could have gotten rid of half of the slide. This is a schema for a clinical knowledge graph. And the red boxes represent that the data is coming from 3 different sources in this schema. One is an Apache Iceberg persistence layer being hosted in the cloud from Tabular.io. Another one is a Postgres database. And the other one is Parquet files sitting on AWS S3. This begins the conversation around a distributed and composite query. Because here we're going to query data not as it was mixed and enriched in a single database, but as it exists in various different data sources, wherever they may be persisted. There. All right, more concretely, what does that look like? In the manifestation of PuppyGraph, a schema is created where the first component you define is your data sources, and that's as part of a data catalog. You'll see here on this slide that at the very top, we're defining a Postgres data source. And then right below that, we are defining an Apache Iceberg data source. You'll note that the Postgres is actually on an EC2 instance somewhere. But here, the Apache Iceberg instance is actually being hosted on the cloud service Tabular.io. So you already have a lot of flexibility of where your data is without having to do the ETL. You'll then define in this JSON schema your vertices. In the vertices, you define where that particular node or label type is coming from. One, in this case, is coming from Postgres, and the other, and many others are coming from the Iceberg data source. Likewise, further down in this schema, you define your relationships. The relationships segment or lay out what node is a pointer from one node to another or a vertice to another vertice, and then all of the properties associated with either the relationship or higher up, some of the properties that are associated with a node. Now, what that looks like in practice is now looking at the JSON representation for the schema, and at the same time, a visual representation of that schema. We can see that the Postgres drug node is represented and is sourced from Postgres. And then likewise, this bioactivity node is being sourced from Apache.io, or I mean, Apache Iceberg from Tabular.io. And then running the query, this is just a regular Cypher query where we do have a where statement that leveraged predicate pushdown in this particular instance in Apache Iceberg. But we were able to surface this insight from these multiple data sources without having to do any ETL. And at the same time, we could quickly begin to experiment on, is this the right schema for the kinds of questions we had to ask? Now, I want to take a moment and go a little bit deeper into that. Right now in PuppyGraph, you load in your schema that we saw earlier. So this representation of the data sources, your nodes, and your relationships. And then you are able to start querying across these multiple data sources. Well, you can imagine that you can also have multiple graph query engine nodes and begin to experiment with your data through multiple lenses, either concurrently or allowing different teams with different use cases or business purposes to concurrently be able to look at the data differently. Or if you only have a single node, you can reload a JSON schema and begin to iterate on how you're looking at the data. You can do the same thing in traditional graph databases, but now you're not going through that iterative cycle of reloading your data. And there is a scaling point at which reloading your data through a different schema becomes a little bit more of a challenge. So the capability of schema on read allows for a lot more prototypic investigation and experimentation and a quicker time to value to, I think, zeroing in on the actual schema that is going to be the most effective for the use case. The composite query nature of being able to look at data and rapidly integrate and enrich a graph by just defining a new catalog and defining the nodes and the relationships across those different data sources also really enhances and amplifies that time to value in a graph project. So we ran this query. You can see the results are here. The nice thing about a graph query engine, or at least in PuppyGraph's case, is that as application developers and solution designers, you don't have to rethink how you are working with the data, because you'll notice it's still using OpenCipher, and now we can start to think about our new standard GQL. Also, it is using familiar drivers. In this case, this is a query ran through the Neo4j graph database Python package, and over the Bolt protocol. So as an application developer, to take advantage of a graph query engine, you don't have to forklift or rethink how you design and develop your applications. Where is this all heading? Certainly, I think that we're going to see some interesting evolution given this decoupling that graph databases are mirroring in what we're seeing in traditional databases. Things like Dremio have certainly, I think, exposed some interesting use cases and capabilities. They've cut costs using commodity storage of data. We're going to start to see the same things in the graph domain. I think that some interesting features will also come out of this, such as we talked about schema-on-read, where you upload the schema and then can query through it. I would like to think that, and maybe we'll see it from PuppyGraph in the future, the ability to actually submit your schema alongside of your query. So it is schema at read at computation time. I think that that would certainly be a capability that would lend itself quite well to many use cases. And I'm quickly running out of time. So very quickly, this is what we covered as some of the advantages of being able to perform composite queries when you decouple the compute from data persistence. And with that, my contact information is here. Certainly can scan my badge or just come find me later at the conference. PuppyGraph, which is the graph query engine that I mentioned, they're here today as well. And this is the contact information for Waymo, it's right there. And then lastly, in the next 5 minutes, I think I will say thank you very much for your attention. Sorry it was so rushed. There's a lot of more detail I will gladly talk to you each about. But right now, what questions do you have?
Thankfully, we have a lot of time for questions, so we'll take one. Either.
Thanks so much. That was actually very interesting. I have a couple of things. One was when you're courses, like, is this all manual? Or just...
Well, yes and no. That's always, it depends kind of an answer. In the first instantiation of this particular solution in PuppyGraph, yes, it's a manual entry, but now they have a actual schema builder, which is much more visually driven through a UI.
And the second question is, how does this deal with like schema evolution?
Mm-hmm. That goes back to, and that's a great segue into your first question. Using the UI tools to develop a schema is really great. It's quick for prototyping. Outputting the schema, though, still is important. Right now in my work, I still save the schemas to a repo and version them.
I think that it sounds like I'm in like investment banking, and I'm trying to those domains like finance and pharma, which have different schemas spread across different sources, for example.
Absolutely. So you're saying when the source data schema has drift?
Yeah,
You'll have to align with that, certainly. But the ability to quickly modify a schema and then use that on an on-read process allows you to have that adaptability a lot more easily. My background is in healthcare, and I've worked with very large clinical databases. Trying to re-ingest or modify a schema is a lot harder than just changing it on read.
I think that ties to like your point towards the end where write the schema at runtime.
Yeah, that to me, I think is the next holy grail. I'm pretty happy with this in the first place. So.
Hey,
Turned on.
Hi, fascinating topic, thanks. So regarding the point you mentioned, when you can link this with any other query engines SDK, like the Neo4j example that you gave, what are the performance implications of that? Because if the query engine is decoupled and it's sitting on top of some other tools SDK, at what stage are we potentially compromising performance, and where are the pushdowns happening? Where is the loss of performance happening?
I think it depends on the actual data source. So I mentioned in one of my examples that you can take advantage of Apache Iceberg expressions. That's where you can actually look for optimizations into query planning at the graph query engine level. In some other instances, you're still going to be constrained by two things. One, the implementation of how the data is persisted, and if that's another database, then yes, you're still constrained by that to some degree. But when you start thinking about working directly with the data through a table manager like Iceberg, and the data is optimized columnar store in a Parquet file, then you have some advantages. So I think it's a give and take.
What's the target initial use case? Is that for batch?
That's right, I can hear. So the question was, what's the target use cases? Is this for batch analytics? It certainly could be used for batch analytics, but it also could be used for, I think, regular graph projects where some of the constraints are you can't move the data for either regulatory security projects. I work in government efforts where moving and ETLing data it's not even part of the conversation. So it has use cases for more than just batch, but it absolutely could be used for on-demand analytics. There's a lot of work being done by companies like MimGraph and others where they are focused on taking different modes of analytics in memory, and graph query engines like PuppyGraph are doing the same thing where you're bringing in just the intermediate results in the final computation for providing that back to a user. That brings up the advantage, or one of the advantages is that you're not constrained on trying to load the entirety of your graph into RAM or into memory. Now, data persisted into different data layers, like on disk, for example. The RAM constraint now becomes, do you have enough RAM to actually hold intermediate results and then calculate the final result that you're going to return to a user? That can be scaled horizontally just by adding additional compute node. Being able to do the calculus of compute math and what you need there resource-wise, aside from and or agnostic of persistence, is going to be a value.
So is that distributed?
There is a distributed where you can have clusters of nodes where you won't need, where you need more RAM for computation, or what I was talking about earlier, not clusters, but multiple instances to simultaneously house different views or schemas into the exact same data, or pick and choose what combinations of the data you want.
All right, so we'll take one question from the online audience, so if you can repeat the question.
Sure. This seems analogous to data virtualization tools such as Donato, which have a semantic layer that corresponds to a schema. The difference being that the query languages and nuances of this schema and semantic layer. Yeah, I think to a degree, I think here though, it's focused more on the decoupling and the advantages of being able to create composite queries across multiple data sources in alignment with what the user, I didn't see the name, presented in the online question. So yeah, I would agree with that.
Final question?
I have a question about the mechanics of retrieving the data. So I see you've connected to the drivers to the underlying data sources and you've mapped the nodes to.
Relationships below, yeah.
Is PuppyGraph doing that translation to query language? So it understands the source requires a SQL query. It understands this other source cipher. So it will do that for you.
No, it's not like GraphQL where you have to actually write those transforms. More importantly, though, it's not just a transpiler. It is going to take advantage of some of the capabilities dependent on the data stores. So it is its own query planner as well, because it has to orchestrate that. The second thing it can do is once you have those results in memory, there's a lot you can do now that you have just the filtered results in memory. You can implement graph algorithms. Right now, they have centrality and a few other algorithms implemented, and that is continuing to grow on a rapid pace. And we're seeing that in other solutions as well, where taking advantage of the data persistence, doing things like predicate pushdown and only bringing back the intermediary results that you need by having those results in memory. Now you can do a lot more with that. Put it internally into a RocksDB or a StarRocks database and perform DGL library computation on it.
All right, with that, let's conclude the session. Thank you so much.